Let's take a look at question 338, counting bits. And bits is something you don't often manipulate, well, at least not in regular web development or software development, unless you're going lower level. So this is a good question just to both get an understanding of how bits work, and it also will teach us a few cool things with bit-related operators. Given an integer n, return an array a and s of length n plus 1, such that for each I between 0 and n, including the answer array for each element is the number of ones in the binary representation of I. So it sounds kind of confusing, but if you look at this example here, let's just straight up look at example 2 here. If you pass in n equals 5, basically we want to have 6 numbers returned. If we pass in n equals 2, we want to have 3 numbers returned, because we also want to include 0. So we include the number 0, the number 1, the number 2, the number 3, the number 4, the number 5. And if you look at the binary representation of each of those numbers, we see that 2 to the power of 0, well, we got 0, and then 2 to the power of 0 as a bit is 1, so that's a significant bit. Then we got 2, where we've got the 2 to the power of 1 as a significant bit, which is 1. Then we got 3, which takes that 2 and then adds on that 1 there. Then we got the 4, which, you know, we've got 2 to the power of 2 now, and then we've got 2 to the power of 2 plus that 1 there. So it's important that you understand binary numbers and how they work. And then let's just dive into actually how this works. So we sort of need to understand the intuition of what's happening here. So what I'm going to do is I'm just going to, just above this function here, I'm just going to write a few things out here, and it will help us see a pattern. So what I'm doing is I'm just taking the numbers 1 to 5, and I'm just writing the binary representation in 4 bits. So your computer probably stores these in 8 bits, but there's a lot of leading zeros here, and they're not necessarily needed to understand this pattern here. So basically what I'm doing here is I'm just writing out the binary numbers. So here we've got 3 and 4. And I'm purposely not putting the arrows on particular ones. And basically what we need to do here is we just need to recognize the pattern here. So this is something we probably don't normally think about when we think about just regular numbers. But binary numbers, they sort of have this pattern. Because if you look at these numbers here, if you look at 0 and then 1 and then 2 and then 3, you'll notice that the time you get back around to 4, that these 2 values are repeating here. And then these 2 values here are repeating the 1, and they'll be a pattern that continues on. And it sort of occurs at each sort of power of 2. Well, the power of 2 is another thing to note, is the power of 2 is sort of like a significant term. So 0, well, 1, 2, 4. We can see that this sort of increments the number to 1, and then all the other numbers are sort of going to be 0. So, you know, we've got 1 here, 1 in this second spot here, 1 in this third spot here. And that's important because all of the numbers after that are going to take that, you know, that spot there, and then it's going to add something on. So number 5, for example, it takes that significant number and then just sort of cycles through down and sort of repeats like that. And we can look at that pattern again for the 2 here. So we see 2 has this 1 here, and then we have this 1 here as well, but then we just have this extra bit here for the 1 there. And you can draw this out, and you can do this for more binary numbers if you need to convince yourself, but essentially this pattern is sort of useful to know, because what it allows us to do is it allows us to sort of think about what like how we can actually count the bits. Because all we're trying to do here is we're just trying to say, well, this has 1 bit here, this has 1 bit here, you know, this one has 2 1s, this has 1 1, and then this one has 2 1s. So that's what all we're doing. We're just returning an array 0, 1, 1, 2, 1, 2. But at each sort of next number, we've sort of already calculated things based on the previous number. So if we just sort of have an addition there and base things off something related to the significant power of 2, we can just easily determine what the ans is going to be. So they've asked us to return ans. So let's just create ans. And we can do this by just creating a new array, which is going to be of the type number. And we're going to just need one extra spot because, as we saw, if we get the number past 5 in, we're going to need to have the 0 number there. And basically what we're going to do is, since we're creating an array like this, we're just going to need to fill all the values. So in JavaScript, everything's sort of undefined at the moment. So let's just make everything a 0. So our array happens nicely. And 0 is going to be the first number because 0 is always included in the return. So there's always going to be 0 bits in that. And then the first answer is going to be 0. But here we can see that we've got this significant bit, which, there's no numbers after this, but if we look at this significant bit, we can see that this sort of pattern occurs here. So we sort of just want to keep track of this value here. So I'm just going to say, and we're just going to let the significant power of 2, I'm not sure if this is the best variable name, but it's sort of indicative of what we're trying to track here. So we're just sort of tracking these values here for the particular iteration that we're on when we loop through things. So I'm just going to put here, this is 2 to the power of 0 to start off with. So essentially what we want to do is we just want to loop through everything. So we can just have a for loop here. And then we want to do some stuff. And then we want to return the ans here. So basically we can actually skip the first value because we've already put 0 in the first spot. And that's correct because there's 0 bits in that 0 number there. So we can actually just skip 0. So we can actually just start I at 1. And then while I is less than or equal to n, we can increment I. So basically what we want to do, and if we're just sort of considering that we're here, basically, this has 1 bit. So how would we work this out? Well, we can work this out sort of based on the previous bit, but then we just sort of need to add 1 to it. So this pattern makes more sense if you sort of extrapolate this out past the first one. Like for example, 4 here, the number 4, you can see that if you just add 1 to that and the bit there, that will get us to here. So likewise, if we're on the 0 here, we just add 1 to that. So we're using the previous power. So in the first case, there is none. Let's say we're here, the previous power would have been that 4 there. So we're using that. And then for this value here, we can just sort of look up this value here. And since we've already calculated the number of ones, or we will calculate the number of ones in here, you can just look up that and then simply add 1 to that. So if I was to just write one more number here, 6, so that's going to be 0, 1, 1, 0. So, and another thing to note is the even numbers, they all end in a 0, and the odd numbers end in a 1, and then zeros just has all zeros. So, we have the value, how many 1s, how many 2s, how many 4s. So we got 1, 4, 1, 2. So 6 is going to be 0, 1, 1, 0. So one thing to note is, see here on the number 5, we're taking the previous number of 1s, say for 4, where there's just 1, 1, and then we're just adding 1 to that. Now, here we don't look at the number 5. We actually look at the last significant term there. So we can see that instead of adding 1 to these two ones here, we can do it based off this value here. So the last significant term, and then the number of bits here will be 1 here. So essentially what that means is if we keep track of the number of bits in our array, so we already know that the first number of bits is going to be 0, but then let's consider that I equals 1. So we'll just say for answer I. So I'm doing this generically, but I'm taking into account number 1, like while we're working through this. Basically, we can take the previous, what we can do is we can take the 0, let's say. So if I take I, and then I just go ahead and minus the significant power of 2, this will already be calculated, and then we can sort of get this from our array. And then as you saw, we can just go ahead and just add that 1 there to that. And then we can just go ahead and we can return that. Now, we've only done this for the first case here. So basically what we need to do is we need to sort of change the significance power of 2. And how can we tell that? Well, basically we're going to have an if condition to be able to tell that and adjust that. But basically, if the I value that we're on is going to be equal to 2 times the significance of the power of 2, then we can make that. So if I just make this 2 times the significant power of 2 here, and if that's equal to I, then I'll just take this here, and we can just set this equal to I. So let's just look at that for a second. So this is all the code, and it's quite simple, but it's more understanding what's happening. That's the tricky part. So basically, if we say we get to the number I equals 4 here, basically the previous significant number would be 2. So you can see that the significant number just doubles every time. So it'd go 1, 2, 4, 8, and so on. So if you take the previous significant power of 2 and then you multiply 2, and that happens to equal the index that you're on, that means that you're on a new significant power. So you can just make the significant power equal to that particular index that you're on. And then you can make use of that when you're doing this part here. And if I go ahead and I just run this code here, we can see that that's accepted. Although I want to cover this in another way. And the reason I'm doing this isn't necessarily for efficiency, but it's just going to help us better understand binary operators and what's happening with the binary stuff here, if anything's a bit confusing. So this is just sort of like another way to solve the same problem. So I'm going to just comment this out here. I'm going to keep all my binary comments at the top there. And I'm going to call this count bits. So let's solve this with some binary operators and bitwise operators. So basically what I want to do here is just start off by making use of an array which is specifically used to deal with binary data. And you might not have seen this in your regular everyday programming unless you're doing some network stuff or some lower level stuff, but also with JavaScript. So basically we can have a uint, an unsigned int, 8 bits array for n plus 1. Now what this is doing is this is essentially making it so, because arrays are usually dynamic in JavaScript. In most other languages, arrays will be static, or you'll have a list, which would be the dynamic equivalent, or a vector or something like that. So basically what this is doing is this is just allocating the amount of memory. So, and as we saw before, we need n plus 1. So this is just allocating in memory the slot 0, 0, 0, so on, up until n, or n plus 1, because you need to include the 0. So that's all that's doing, but this is specifically a type that's going to be helpful with our binary numbers here. So then what we do is we also have a for loop. So I'm just going to copy this part of the for loop here. And I'm just going to let I equal to 0 in this case here. And this is going to be the result. So this is going to be the result less than the result length. Actually, I might call this answer. Answer length. So basically what we want to do in this loop here is we just want to, and I'm going to explain this in a second, but basically what we want to do is we want to do a similar sort of thing as we did before, where we were assigning the particular, as you see here, that's going to equal, but this time we're going to use some bitwise operators, so bitwise shift right operator. And I'm just doing this just to sort of expose you to the different things you might not normally see. So this double, what is this? Double less than symbol is bitwise right, bitwise shift right operator. And then we can just go ahead and we can just plus on this I and 1. And this is a single ampersand, and this is a bitwise AND operator. So of course I'm going to explain this, but I just wanted to return, and because we need to return a number array, we can just take this uint array and then we can just sort of spread it out so then it's going to be in the right form for us. So we can just take that and return it like that. And you can see that this is much shorter, but to be able to, it's much shorter, but you have to sort of understand binary to a lower level to be able to understand this, and bits to a lower level. And this is why I also wanted to do it and talk about this. In addition to this problem, this algorithm that we solved here, like we need to understand what this is doing and what this is doing here. This part here where you got this uint8 array, let's just think of this as like a number array, but for binary numbers. So that's not really the tricky part. The tricky part's all on this line here, line 12. So let's go ahead and explain this. So essentially what a bitwise shift right operator does, it essentially halves the value and then rounds things down. So I'm just going to delete these sort of significant values here because we've already discussed that approach. But basically, well, this is going to make more sense if we look at the number 2 here, for example. If we move this binary number, if we shift it right, if we do a bitwise shift right, basically we want to take the numbers and then move them to the right. So this would become 0, 0, 0, 1, and then we exclude the last number there. So that means like this would be 0, 0, 0 again. This would be 0, 0, 0, 0 because this last bit has been shifted to the right. And then if we look at this one here, this would be 0, 0, 0, 1 again. And then if we look at 4, for example, and I might just do this up to 5, so it's not too many. So if we do 0, 0, 0, 1, and then we have 0, 0, 1, 0, and then you would have the number 0, 0, 1, 0. So let's look at this. We see that 2 and 3, they're going to be the same numbers. And this is actually just giving you back the number 1 again. And then this is giving you back the number 1 again. And this is giving you back the number 2. And then this is giving you back the number 2. So what this does is, you know, because we've got this like binary sort of number thing, it has this pattern where if you shift things over to the right, it essentially halves the value, but it halves it, but it also rounds it down. So half of 2 is 1, 3 divided by 2 is 1.5, but if you round that down, it'll be 1. 4 divided by 2, that's going to be 2. 5 divided by 2, but rounded down is also going to be 2. So we need to keep this concept in mind because that's what we're doing. But the other thing to keep in mind is the bitwise AND operator. So this is used to determine if, we have an odd number or even number. Well, in our case. But the bitwise AND operator, what this is doing, so let's say you have 3 and 1, bitwise AND. Basically, what we do is we look at 3, and we see we've got 0, 0, 1, 1, and then here we've got 0, 0, 0, 1 for the 1 number. It sort of behaves similarly to the AND operator, but it returns the bit where both of them have bits assigned to 1. So we can see that if you look at that and you look at that, only the last number has the value 1 there. And then they'll give us back 0, 0, 0, 1. So if we just do one more example, we'll do it for the number 2, bitwise 2 and 1. This is going to see we got the 0, 0, 1, 0, and then we got the 0, 0, 0, 1. None of those match, so then we'll end up with 0, 0, 0, 0. So basically, this is going to be true for anything because if we look at the number 1, it's going to have all zeros except for the last digit. So if you do a bitwise operation with anything with 1, if it's an odd number, meaning that it ends in a 1, you're simply just going to get the value 1 because all other bits before it are going to be zeros. However, if you look at any even number, the even number will never end in a 1, so it'll always end in a 0. So that 0 and 1 at the end cannot overlap. And since zeros are everywhere else in the 1, preceding the last digit there, an even number is always going to be, well, an even number with a bitwise AND operator is always going to be 0. And if it ends in, if it's odd, it will be a 1. So hopefully that makes sense. So now with those two concepts in mind, we can sort of return to our line here, which is what we're concerned about. So basically, if we think about this, if I is going to be equal to 0, basically, well, what that means is we're going to have 0 shifted over 1. So we see that the 0 shifted over 1 is still going to be 0. And then, of course, that's going to have 0 bits stored in there. And then, of course, if we have this part here is just to tell if it's odd or even. So as we've seen here, if it ends in, if it's odd, well, if I is an odd number, it will result in a 1. Otherwise, it will result in a 0. So 0, if it's 0, meaning that the whole first part here will be 0. And that's what we expect because, because there's nothing there, right? There's no number of bits for the 0. But let's consider the next case where I is 1. So if I is 1, basically, if we take a look at the previous value, we can see that I bitwise shift right operator will get us to the 0 there. And we know that since we've just calculated that as 0, that's going to be 0. But this time 1's going to be odd. So then we can calculate the number of bits for that. And this whole answer here is going to be 1. So we've got 0 and then 1, which is in line with our previous answer. So I might just run through this a few more times just to really send the message home. But if you got I is equal to 2, basically here we see that we've got this 2 shifting over, so it essentially halves it. So we'll have that value 1 there. So then if you look at the value 1 from the previous thing, there's going to be one thing there, but then it's an even number, so this will value to 0. So then you'll have that 1 there. And then 3, well, this will be the last, actually I might go up to 4 because 4 will have 2. So if we look at 3, right shift bitwise right, this is going to be equal to 1 again, and then that 1, but this time we're sort of adding on that last one there. So then you're going to get 2 1s there. So hopefully that's starting to make a bit of sense there. And if not, you can just sort of draw more of these out and just sort of work through all these cases there. It is a little confusing if you never work with binary numbers, but again, that's why I wanted to sort of show it and display it, just to sort of expose this part of algorithms and stuff like that. But of course you could work it out like that, but in either case you still need an understanding of binary numbers, so you may as well just have be armed with the knowledge of a couple of these operators here. And that's all I really wanted to show. So let's just go ahead and submit this here, and we see that beats 55%, so that's pretty good.